all had a nice coffee break with a cinnamon bun. And let's continue with the real part of this conference by talking about magic and virtual threads. So welcome on stage, Balkrishna Rawool.
Good morning. Good morning. Thank you all for being here, and thanks for the introduction, Clara. So we're going to discuss continuations, the magic behind virtual threads. Well, virtual threads, as we know, has been released as a final feature in Java 21. It is an important feature of Project Loom, and it promises to bring high scalability with an easy-to-use API. But the real hero of the story is actually continuations. Continuations is the magic that powers virtual threads to provide this high scalability. And that is exactly what we're going to discuss in this talk. But before I begin, I want to do a quick poll in the room here. It's quite big. So please raise your hand if you are using at least even one application with Java 21. See how many of you are doing that. That's maybe like, OK, 40% of the room. OK, I could expect a bit more. So you have the ability to use virtual threads in your applications. So keep your hand raised, or still raise your hand, if you have been using virtual threads, at least in one of the applications. OK, that's pretty less, maybe 15%. That's OK. Could be more. But thanks for raising your hands. So in this talk, what we're going to do is actually this talk is divided into 3 parts. In part 1, we get a little introduction to virtual threads. In part 2, we understand continuations. We discuss continuations a bit. And then in part 3, we use this understanding of continuations to create our own version of a simple virtual thread. So let's get started. OK, but before we start, a very quick intro about me. My name is Balkrishna Rawool, and I work for ING Bank. So with that, let's start with the first part of the talk, which is introduction to virtual threads. Now, what we see here in this picture is actually an instance of JVM, which is running on some operating system. The JVM has a lot of virtual threads, but also have some platform threads, and OS has some operating system threads. So let me grab some water. OK. So let's first start with platform threads. Now, platform threads are actually a thin wrapper over operating system threads or kernel threads. What that means is when JVM wants to create a new platform thread, it actually requests OS to create a new OS thread. And only when that is possible, it creates a new instance of platform thread. And because of that, these platform threads, they map to OS threads with this one-to-one mapping. Also, creating a platform thread is a resource-intensive task. You don't want to do that too often. So when you are done with the platform thread, you don't throw it away. You put it in a pool. So platform threads require thread pools. And therefore, the next time when you need it, you use it from the pool. Now, virtual threads, on the other hand, are lightweight user threads. Lightweight, meaning they require significantly less memory. And because of that, you can create them in abundance. You can create thousands or even millions of virtual threads. And that makes them highly scalable. There's actually one more thing that makes them highly scalable, and we will see that on the next slide. But one more thing to notice about virtual threads is that they don't need pooling. Because creating a virtual thread is a cheap operation. You can do that whenever you want. So when you're done with the virtual thread, you can just throw it away. And the next time when you need it, you can create a new one. Now, if you look at this picture here, you see a large number of virtual threads and some platform threads. But some of these virtual threads are connected to platform threads. Why is that? Well, that is because a virtual thread on its own cannot execute anything. It requires a platform thread to execute something. But there are some other virtual threads which are not connected. What about those? Well, for those, we have a virtual thread scheduler. So this is a newly introduced scheduler. It is introduced along with virtual threads. And what it does is it mounts a virtual thread onto a platform thread when a virtual thread requires platform thread, and it unmounts it when the virtual thread does not require platform thread. Now, what would be the scenarios where a virtual thread would not require platform thread? It would be when a virtual thread is waiting for something. Let's say it is waiting for a network resource to be available, or a database to return something. Now, in those scenarios, virtual thread does not require processing. It does not require platform thread. Does not require CPU. So it gets unmounted from the platform thread. In a typical I/O-bound application, threads spend a lot of time waiting. Now, all of that waiting can be avoided if we use virtual threads. So if we use virtual threads, only the virtual threads would be waiting, not the platform threads, and therefore CPU is not blocked. and therefore CPU is highly efficiently utilized, and that's what makes virtual threads highly scalable. Now, we'll see that in action when we, in the later part of this talk. But one more thing to notice in this picture is that the platform threads in this entire endeavor of mounting and unmounting are carrying virtual threads. Therefore, they are also known as carrier threads. OK, that's a lot of theory. Now, let's see virtual threads in action. Let's create some virtual threads. For that, I'm going to head over to IntelliJ. And I hope you can see that. But the font is really small, so let me zoom in a bit. I hope you can read it in the back. Yes? No? OK, let me zoom in even further. Oh, it went back. Is this OK now, or? OK, I get a yes, so I'm going to continue. OK, so let's create some virtual threads. But first, let's create a platform thread. With Project Loom, there is actually a new API. So we could do thread.offPlatform. And that gives us a platform thread builder, onto which then we can call start and pass a runnable. And in this case, I'm just going to print the current thread. So this will create a new platform thread. Let me run this and see that it actually creates a platform thread. Oh, I'm running the wrong test. So let me do it once again. So thread.offPlatform.start and pass a task to it. Just print the current thread. And now if I run this, I should see a platform thread. There we go. OK, so similar to off-platform, you can imagine another API to create virtual thread, which is off-virtual. And so this gives us a virtual thread builder, onto which then we do start, and that gives us a virtual thread. So let me run this, and that should give us a virtual thread instance. Now, if you look at the two-string representation of the virtual thread, there are a couple of things we can notice. One is that, well, this part, which is actually called the ID of the virtual thread, and it is unique for each virtual thread instance. And then this part, which is actually the platform thread onto which this virtual thread was mounted when it executed this statement. So you get some information about the carrier thread as well. There is also a shorthand method. So you could simply do start virtual thread, and that gives us a new virtual thread, and it starts it as well. OK, there's actually one more way to create virtual thread, and that is to use executor service. So let me do that. Try executor is nothing but executors.new virtual thread per task executor. So what this does is this gives me a new executor service, which is not backed by a thread pool. So it gives a new instance of virtual thread every time I request it. And the way to do that is just do executor.submit and submit a task. So in this case, again, I want to print the current thread. So this will do the same thing, give me a new virtual thread like so. OK, now I can actually create a bunch of these virtual threads. So let me do that. And because I'm using try with resources, it will ensure that all these virtual threads are finished before I exit this try block. So now let me run this and see what happens. So it gives me a bunch of virtual threads. And if you look at these IDs, they are all different, meaning that all these virtual threads are different virtual threads. But if you notice here, for example, you have the same platform thread. So what is happening here? This virtual thread got mounted onto this platform thread. And when it was done, it got unmounted, and a new virtual thread got mounted onto the same platform thread. So basically, we see that mounting and unmounting in action here. And this mounting and unmounting, how does this happen? What does it mean for a virtual thread to get mounted on the platform thread? And because this is actually driving the high scalability behavior, what is it that gives high scalability to virtual threads? And the answer to those questions is continuations. So here we start part 2, where we discuss about continuations, what they are, what are they useful for. So let's first see what is a continuation. So a continuation can be viewed as a representation of the current state of the program. So your program could be as simple as some sequence of instructions, or it could be a bit more complicated with nested method calls or nested loops. And you can take continuation at any point in time, and that continuation object would represent the current state of the program, including the method that you were at, the nested method call, including the iteration of the loop that you were at when you took that continuation. So when you take the continuation, your program is paused there, and then you get a handle to the continuation, and then you can pass that object anywhere in the program, and then you can decide to resume the program at that point. So it then resumes there and continues until its completion. So you can think of continuation as the rest of the program or the rest of the computation. So effectively, you can imagine continuation as a representation of the current state of the program or the rest of the computation. Because what is the use of such a continuation? Well, it allows us to pause the execution of the program and resume it later. Now, we'll see that in action in a bit when you look at continuations in Java. But before we do that, I want to highlight something, and it is that the continuation API in Java is not supposed to be used by application developers directly. So right now, it is only used internally, and it is only used to create virtual threads. But then you might ask, why are we discussing it? Well, 3 reasons. One is that understanding continuations would give us good insights in the behavior of virtual threads. It would help us understand how mounting and mounting happens, basically what is it that is driving this high scalability characteristics of virtual threads. And thirdly, because it is fun. So let's go ahead and see some examples with continuations in Java. Again, I'm going to head over to IntelliJ. And let me create a continuation. And let's say we get that from a method called getContinuation. And let me create that method. So this method returns a continuation. But hang on. I just said that continuation API is only available internally. How am I able to use it here in my application? Well, that is because I have asked the compiler to expose everything from java.base module. Again, if you see this for any program, then it is an indication that this code is not supposed to reach production. So don't do this for your code that you want to run in production. I'm doing it for now only because I want to experiment with the continuation API, and I want to see how it behaves. So for now, it is OK. So let's create a new continuation. This would be new continuation. And continuation requires continuation scope and runnable. So let's create continuation scope first. So continuation scope, for the purpose of this talk, you can think of it as a namespace for your continuation. And here I need to pass a string. It could be anything. It could even be empty. Let's say demo for now. Pass that scope, and it requires a runnable. So in this case, let's just say this runnable prints a few things. So it prints A, prints B, and it prints C. And then I return the continuation here. And here, well, I have the continuation. What can I do with it? I can run it. OK, so let's run this program and see what happens. If I run this, I see A, B, C being printed on the console. So what is happening is, basically, running the continuation has simply run the runnable. There is nothing fancy going on here. But because this runnable is wrapped in a continuation object, we get certain power. And the power is to pause the execution of this runnable. And the way to do that is actually to call continuation.yield, and then pass the scope. Now, I want to do that at 2 places, here and here. So now, let's run this and see what happens. It prints A. So what has happened is, it basically ran the runnable, and it executed this statement, and then it encounters this yield call. And that pauses the execution of the runnable. And it also transfers the control all the way back to the point where the continuation was started. In fact, immediately after continuation.run call. So I could actually do something here. And then what it will do is it will basically execute this statement after this statement. So let's see what happens here. So running the continuation runs the runnable. It executes this statement. Then it encounters this and pauses the execution, transfers the control all the way here, and then it does this. That's what we see here in the console. OK, the runnable is paused. How do I resume? Well, I can simply call continuation.run once again, and that will resume the execution of the runnable. So when we do this resume, it actually takes the control all the way back to the point it was paused, and then it resumes from there, and it starts executing those statements. So then it executes this statement, and then it encounters another yield. So it basically pauses the execution once again. So resuming the continuation takes us back to the last yield point, and then from there, it takes us to the next yield point, and then transfers the control again here. So let me resume it once again. That basically finishes the execution of the runnable, because there is nothing else here remaining in the runnable. And again, what happens if we run the continuation after it is completed? Let's see what happens. Run it once again. If I do that, I get an exception which says continuation is terminated. So once the continuation is completed, we cannot resume it further. Let's not do that for now. But there's actually an API to check if a continuation is completed or not. There's a method called isDone. We will see that a bit later. But for now, let me just run it until it is completed. And that's what we see in the output. So basically, this is the way to have a runnable and pause and resume its execution. Now, before we move on, I want to highlight a couple of things. One is that this call, continuation.yield, it does not have to happen from the body of this runnable. So it could be it could be somewhere in nested method calls. And in that case, the execution would pause at that point. And it would transfer control all the way back to the point where continuation.run was called, in fact, immediately after it. Secondly, this call, continuation.run, again, does not have to happen from the body of this method. So when you create a continuation, you get this object which represents current state. And then you can pass that object anywhere in your program, and then you can decide to resume the runnable at that point. OK, so this control transfer, it feels a bit abrupt, right? So how does this happen? Let's explore this with the use of another example in the slides. So let's first explore what happens when you call continuation.yield. So this is the point where the execution of the runnable is getting paused. How does that happen? Well, we'll explore that with an example, a simple example, where we have a main method which calls method A. And A creates a new continuation, and then it runs the continuation. And in the continuation, we are calling another method B. And in method B, we call method C. And method C is the one that does continuation.yield. So at this point, the execution should pause, and it should transfer the control all the way back to method A, because that's the one that did continuation.run. So how does that happen? Now, this is happening actually mainly with the manipulation of call stack. So let's look at the stack memory. And in this case, this memory is getting filled from top to bottom, sorry, bottom to top. And we have heap memory, so we also explore what happens there. So when we call main, we get a new stack frame on the stack for main. And main calls method A. And method A actually creates a new continuation object, which we see on the heap. And then method A does continuation.run, which calls method B, that calls C, and C does continuation.yield. So this is where the continuation should pause, right? And the control should get transferred to method A. So how does that happen? Well, all the stack frames on the stack from continuation.yield until B, they are moved. They are moved to heap, and they are saved inside the continuation object. And then the top frame on the stack, which is continuation.run, that returns to method A. And that's how you effectively transfer the control to the method A immediately after continuation.run. OK, so this explains how the runnable is getting paused. But how is the runnable getting resumed? Well, we look at the same example, but we extend a little bit more. So here we explore continuation.run call. Again, we have the same method, main, which calls method A. But after that, it also calls method D. And we have the same method A, B, and C, doing exactly the same things as we did in the previous slide. And we have method D as well. So what does it do? It does continuation.run. And it is the same continuation object that was created in method A. Now, when continuation.run is called, it should actually resume the continuation. It should take us back to the point where it was paused, and then resume from there. How does that happen? Again, we explore stack memory and heap memory. Stack is getting filled from bottom to top. Heap memory as well. So in this case, on the heap, we already have continuation object with the stack frame saved in it. And on the stack memory, we have main, which called method A. And now method A resumes its execution and finishes, and then main calls method D. And then D calls continuation.run. So this is the point where it should actually transfer the control to the last yield point, which was the point where the continuation was paused. So how does that happen? Well, all the stack frames which were saved in the continuation object, they are now moved. They are moved back to the stack, and the top stack frame, which is continuation.yield, that returns to method C. And that's how you effectively transfer the control to the point where it was paused, and then you can resume from there. OK, so this control transfer, it is a bit wacky. What is it good for? What are the uses of this? Well, there are many uses, including these 4 things. So you can implement virtual threads using continuations, but you can also have your own version of coroutines or exception handling or generators. Now, in this talk, we're actually going to explore 2 of these uses, starting with generators. So we'll see how we can implement generators using continuations. And then in the third part of the talk, we'll also see how we can implement virtual threads using continuations. So let's start first with the generator. Well, first, what is a generator? A generator is actually a data structure that allows us to write a function that returns multiple values, or that yields multiple values. So typically, when you have a function, it returns one value. But with generator, you can write a function that returns multiple values, and not all of them at once. So these values are lazily retrieved. And you can also iterate over these values by using a loop, like in this example here. So here you have a generator, which is yielding A, B, C. And then you have a consumer, which is basically using a loop to iterate over these values. Now, when would you use a generator? Let's say you have complex calculation or resource-intensive tasks, and only after that you can yield some values, right? So you don't want to do all of that upfront. You only want to do the calculation which is necessary for the values that you need. And that's when you would use a generator. Now, implementing a generator in Java is not that difficult. You can use streams, because streams are lazily evaluated, and streams deal with multiple values. So you can easily implement generator using streams, or using iterators, or a collection of suppliers. But in this case, we're going to implement generator without using any of these things, but only using continuations. So let's see how we can do that. OK, I'm going to move to IntelliJ. And what I want to be able to do is to create a new generator like this. So new generator. And let's create this class. So public static class generator. And our generator should yield values of certain type. And let's say they are of type T. And in our case, we want strings to be generated. So let's say this is a generator of strings. And we want to implement generator using continuation. So let's add that, create a private continuation. And continuation requires continuation scope. So let's add that here. OK. And now let's write a constructor. Here we're going to basically initialize these things. So scope would be new scope with any string. Let's call it generator. And the continuation is going to be new continuation with the scope. And it requires runnable. Let's say the runnable is empty for now. And then we run the continuation. OK. And now, actually, what we want is we want a generator to have this logic. Now, we want a place to write this logic. So let's say the input to the generator is a lambda, which allows us to write that logic to yield A, B, and C. But that's not how the yield keyword in Java works. So we cannot have our implementation exactly same as the pseudocode that we saw on the slide. So let me get it to as close to it as possible. Let's say we have a yield method, and to which we can pass the string. So that way, we can make these yield calls, and then pass A, B, C to it. And let's say this yield method is available to us on an object called source. So we can do source.yield. Now, hang on a minute, and this will make some sense. Then we have source.yield again, source.yield here. And let me define a source type. So public class source. And create a private member variable here of type source. And initialize the source here. And now, the argument to the constructor of the generator is a consumer of source. So this is a consumer of source called consumer. And in the runnable, I'm just going to do consumer.accept. Oops. Consumer.accept. And pass the source. So that way, this lambda gets executed. And now the only thing that is remaining is basically to implement this yield method, which I'm going to do here. So after the yield is called, we want the execution to pause, right? We don't want to yield all the values at the same time. So the way to do that is to call continuation.yield, and then pass the scope to it. And we don't want to lose this value, so let me put it in a private member called value, and then store it there. So value equals t. And now we are basically able to define the generator, but we should be able to use it in a loop. So let's say we have a couple of methods on the generator, which allow us to use it in a loop. So in this case, let's say we have hasNext method, and we have next method. Now, implementing hasNext is not that difficult, because a generator has values as long as the continuation can continue. So we could simply do continuation.isDone, and in fact, negation of it, because the generator has values as long as the continuation is not done. And then the next method would simply return the value that was present in source. So we could do return source.getValue, and let's write the getValue method here. Let's make it private. And now I want to resume the continuation here. But we can't do anything after return, so let's put it in a temporary variable and then return the variable here. OK, so now we have the generator completely written and also used. Let's run this and see what happens. It should basically yield all these values, and it has done that. So basically, it is now yielding these values, and every time it yields a value, it pauses the execution there, and it transfers the control all the way here. So I can actually do something, and it will do that every time it yields a value, every time in this loop, like so. And in fact, I can decide to terminate the loop at any point in time, and that would basically only execute the part of the generator that I want and not the rest of the things. Okay, so this is how we can implement generator using continuations. Okay, I will share the link to the source code so you can take a look later. But I wanted to include this example of generator using continuations, because I wanted to highlight the fact that continuations is a general purpose utility. So it is useful for virtual threads, but it is also useful in other scenarios. Okay, so let's move on to the last part of this talk, which is basically implementing virtual thread using continuations. Now, our simple version of virtual thread, it should have certain characteristics for us to be able to call it a virtual thread. And those are goals of our exercise. So what are the goals? A virtual thread instance should not use CPU or platform thread when it is waiting or when it is blocked. Okay, that sounds reasonable. Also, a virtual thread can get mounted on several platform threads during its lifetime. And a platform thread can support several virtual threads during its lifetime. So basically, that man-to-man relationship between virtual threads and platform threads should be evident from our implementation of virtual thread. OK, these sound pretty reasonable. Let's go ahead and see how we can implement those. So what we'll do is we'll create a new virtual thread class. Then we'll create a consumer, which is basically using this virtual thread. So we'll create a bunch of virtual threads, which will also have some blocking calls. And we will have a virtual thread scheduler, because we want to schedule these virtual threads onto platform threads. So this scheduler will have a bunch of virtual threads and a bunch of platform threads, and it will schedule these virtual threads onto these platform threads. Okay, this again looks like a pretty logical design for our implementation. So let's go ahead and implement that. I'm going to head over to IntelliJ, and let's start with creating a new virtual thread class, virtual thread. Now, a virtual thread in its most simple form is nothing but a continuation. Of course, it requires a scheduler to execute it, but if you externalize the scheduler part, what remains is nothing but continuation. So let's add that here. Private continuation, continuation. And continuation requires continuation scope. We know the drill. But in this case, I want to make it public static final continuation scope called scope, and then initialize it here already. Virtual thread. OK, and now I want to write a constructor. This would basically initialize the continuation, new continuation, pass the scope, and it requires runnable. But let's say we get the runnable as an argument to the constructor, and then we use it here. And we want to be able to run our virtual thread, so it requires a method run. We add that here. What it does is it first says that virtual thread is running on, and then it says which platform thread it is running on, and then it basically runs the continuation. OK, this is actually complete implementation of the virtual thread. This is sufficient. This should be enough to have our virtual thread. But I want to add something else to it in order to make it more useful, and that is ID of the virtual thread. So I'm going to add private int ID and have a private static final atomic integer to set the IDs called counter, starting with a value of 1. And then I'm going to set the ID here. So this would be counter.get and increment. And then I can also print the ID here. So I know which virtual thread is running on which platform thread. There we go. So we have our virtual thread implemented. Let's go ahead and use them. Let's create some virtual threads in a class called demo. So demo is going to have a main method that's going to create a bunch of virtual threads. Let's say new virtual thread. And what this does is it prints a few lines, 1.1, 1.2, 1.3, and 1.4. We can think of this as instructions that the virtual thread is executing. And I'm going to have one more virtual thread called VT2. And this is going to, again, do exactly the same thing as virtual thread 1, except that it's going to start the instructions with this number 2. OK, so we have our virtual threads. We have virtual thread class. We have some virtual thread instances. But we need a scheduler to execute these. So let's create that scheduler. Virtual thread scheduler. And if you remember the picture here, so scheduler has a bunch of virtual threads and a bunch of platform threads. And it schedules these virtual threads onto these platform threads, typically in a first-in, first-out manner. And therefore, it would be handy to have these virtual threads in a queue. So let's put them in a queue. Let's say we have a private queue of our virtual threads called queue. And this would be a concurrent linked queue. And for the platform threads, I'm just going to use a plain old executor service, which would be a fixed thread pool of 3 threads. OK, now I want to be able to start the scheduler. So let's add a method, public void start. And what the start does, it runs forever. And it checks if there is something in the queue. And if there is something, it picks that thing up. And then it submits it to the executor to execute. So basically, what this method is doing is it is constantly looking at the queue. And whenever it finds something, it picks that thing up and gives it to the pool of platform threads to execute it. OK, now we want a method to add new virtual threads to our queue. So let's create a method called schedule, which takes virtual threads. And basically what it does, it adds the virtual thread to the queue. That's it. This allows us to schedule new virtual threads. OK, so we have a scheduler. Let's use it in the demo so we can actually run this virtual thread. So I'm going to create a public static final virtual thread scheduler called scheduler. This will be a new scheduler. And let it run it in its own thread. So we have a new thread, scheduler start.start. OK, and now we are able to schedule these virtual threads. So we could do scheduler.schedule VT1 and VT2. OK, now let's run this and see what happens. So here we have 2 virtual threads. And the scheduler has 3 platform threads. So when we run this, each virtual thread would get their own platform thread, and they would start running in their own threads. So let's see if that actually happens. So when we run this, what we see is that virtual thread 2 is running on platform thread 2, and virtual thread 1 is running on platform thread 1. And they are running in their own threads parallelly. Now, what if I want to run them sequentially? I could actually just change this number of platform threads to 1. And that would mean that there is only 1 thread, therefore they can run sequentially. So we have virtual thread 1 running on platform thread 1. Then it runs to its completion. And then we have virtual thread 2 running on platform thread 1, because there's only 1 platform thread. And that runs to its completion. OK, let me change this back to 3. And then add a blocking call in this equation. So when the OpenJDK team worked on virtual threads, they created the virtual thread, but they also made the entire JDK aware of this new implementation of virtual thread. So all the places where there were blocking calls happening, they made those places aware of the virtual thread. Now, we don't have enough time to change the entire JDK to be aware of our virtual thread. But what we're going to do is we're going to create a simulation of a blocking call. But before we do the simulation, I want to add one more feature here, and that is thread.currentThread. So right now, when you do thread.currentThread, you get access to the currently executing platform thread. But I want something that gives me the currently executing virtual thread. So for that, I'm going to add a static member here, public static virtual thread called current virtual thread. Now, I have a question, because there's not going to be one virtual thread. There will be multiple virtual threads. In fact, there will be one virtual thread for each platform thread. Each platform thread would be executing its own virtual thread. So the question is, what would be the type of this variable? Because this variable would have different values for each platform thread. Does anybody know what would be the API that you would use for a variable that can have different values for different platform threads? Any guess? So you have a variable which can have different values for different threads, different platform threads. What would we use in that case? Thread local, exactly. So we could use a thread local here. So if you use thread local, then we would have this variable, which would have different values for different platform threads. But there's actually a new API available in Project Loom, which is a better alternative to thread locals. Does anybody know what that API is? Scoped value, exactly. So I'm going to use scoped value here, and also make this final. So scoped value is a better alternative to thread locals. It is a preview feature, so when it is there, you could basically replace your thread locals with scoped value. So this would be scoped value dot new instance, and then the only thing that is remaining is to make sure that this scoped value is set to the right virtual thread, and I'm going to do that here. So this would be scoped value dot where this is set to this virtual thread, run the virtual thread. OK, so what this is doing is that basically, before running the virtual thread, it sets this scope value to the right virtual thread. So we get access to the currently executing virtual thread. OK, so now that that is done, we're going to add the blocking call in this equation. And we're going to call that class waiting operation, because a blocking call is indeed a waiting operation. And this has a public static method called perform, which performs the waiting operation. And it takes two arguments: name of the thing that it is waiting for, and duration in seconds that it is waiting for. And the first thing that it does, it prints saying waiting for this thing, for duration amount of seconds. OK, now when the virtual thread is performing waiting operation, we want the execution to pause. And the way to do that is call continuation.yield. And then pass the scope here. In this case, this is virtual thread.code. Let me do a static import for this. So now, basically, we have paused the execution. But we also want to resume it at the point when the waiting is over, when the duration is done. And for that, I'm going to use timer. But actually, there are better APIs, better alternatives than timer. But timer is good enough for our use case, so I'm just going to use that. Timer.schedule a new timer task. And I'm going to basically execute it after the duration amount of seconds. And I shouldn't forget to cancel the timer here. And now this is the point where I want to resume the virtual thread. But which virtual thread, you ask? Well, it is the virtual thread that was executing this call, this method. So I should get a currently executing virtual thread here, which would be virtual thread is virtual thread scheduler dot current virtual thread dot get. So that gives me access to the currently executing virtual thread here. And then I can basically resume this over here. And that would be demo.scheduler.schedule this virtual thread. Let me do a static import for this. So that way, we have our simulation of a blocking call implemented. Now, let's use that in our virtual threads. So let's say virtual thread 1 is waiting for, let's say, network for 2 seconds. and virtual thread 2 is waiting for database for, let's say, 5 seconds. And now let's run this and see what happens. So what will happen is basically, again, we have 2 virtual threads, and I think we have 3 platform threads. Yes. So each virtual thread would get their platform thread, start executing, and execute these 2 statements. But then they'll encounter this waiting block. They'll encounter this blocking call. And at that point, they will get unmounted from the platform threads. And now there are 3 platform threads still available for a new virtual thread. So when this virtual thread comes back after the waiting, it will have all 3 platform threads available. It can pick any one of them and resume its execution. And when this virtual thread comes back after 5 seconds, it again has the 3 platform threads available, and it can take any one of those. So let's run this and see if that is exactly how it works. So what we see is virtual thread 2 is running on platform thread 2. Virtual thread 1 is running on platform thread 1. And then they both execute these 2 statements. And then they start waiting. And after the waiting, virtual thread 1 is running on platform thread 3. So a totally different platform thread. And then it runs to its completion. And then virtual thread 2 comes back, and it starts executing on platform thread 1. So now let's see what has actually happened here. Let's look at this virtual thread. So virtual thread 1 was running on platform thread 1 before the waiting. And after the waiting, it is running on platform thread 3. So basically, it has moved from one platform thread to the other platform thread. So that's one virtual thread supported by 2 platform threads. And if you look at this platform thread itself, it was running virtual thread 1 before the waiting. But after the waiting, it is running virtual thread 2. So it was supporting one virtual thread, and after the waiting, it is supporting a different virtual thread. So basically, we see that many-to-many relationship between virtual threads and platform threads. So we have all the criteria that we set for our virtual thread achieved here. So we have a simple implementation of a virtual thread. But hang on, this is a virtual thread. And we said that with virtual thread, we can create them in abundance. We can have a large number of these virtual threads. So let's see if we can do that. Let's turn the heat up and see if we can have a large number of the virtual thread that we have created. And I'm going to say, create 1,000 of these, if not millions. And so what this will do is this will create 1,000 of these virtual threads, 1,000 of these virtual threads. So basically, 2,000 virtual threads running on, let's say, 10 platform threads. And that'd be a problem. I think in the waiting operation, we have this timer task. This uses platform threads, so this could be an issue. But because these are a few thousand, maybe it wouldn't be. So let's see what happens if I run this. So with 2,000 virtual threads running on 10 platform threads. But before I run this, I want to actually show you one more thing, which is I have another demo class, which looks quite similar to this class. In fact, it is exactly the same. The only difference is here I'm using virtual threads, and here I'm using runnables. So the one on the right-hand side does not use virtual threads. It uses runnable. But these runnables do exactly the same things. So I have this first runnable, which waits for 2 seconds after some instructions. And I have 1,000 of these. Again, I have 1,000 of these, which are waiting for 5 seconds. So I have now 2 implementations. The one on the left is using virtual threads. And the one on the right does exactly the same thing, but it is using runnables. It is not using virtual thread. And the scheduler here also has 10 platform threads and no virtual threads. OK, so same scenarios, but one with virtual thread, one without. So let me run first the one without virtual threads, and let's see what happens. So it runs, and runs, and runs. And it will go on running. It is a bit boring, so I'm just going to put it over here on the right-hand side. And while that runs, I'm just going to run the one on the left-hand side, the implementation that uses virtual threads. So if I do that, it runs, and runs, and something has happened. I actually see this virtual thread 2,000, basically the last virtual thread that we created. It has executed last instructions. So basically, all the virtual threads have finished executing all the instructions with all the waiting. But the one on the right-hand side is still going on. So what we see here is that with virtual threads, we can actually get much more done with the same amount of CPU, provided you have sufficient waiting in your application. So this is actually the high scalability promise of virtual threads. And the right-hand side implementation, it just goes on. And on my machine, it takes 15 minutes to finish. So let's move on to the slides. So that was actually the last thing that I had to show. And all the source code is present here. Also, if you want to reach out to me on the social media, you can reach out to me there. And if you did like the talk, then you can also rate it nicely. But where, you ask? Here. That's the QR code for rating this talk. Yeah, that's it. Actually, let me just quickly summarize what we discussed in this talk. So we started with a quick introduction of virtual threads. And then we looked at continuations. And then we used that understanding of continuations to create a simple implementation of a virtual thread. And in doing so, we got good insights in the behavior of virtual threads. We also got to know how mounting and mounting happens, and basically what is it that is driving this high scalability benefit of virtual threads. And I hope it was fun. Thank you.